Welcome to the MOOCs course, Mechanical Unit Operations. The title of this particular lecture is Screening Equipment, Effectiveness and Capacity. Screening equipment. The screening may be carried out in different types of equipment. So, it is basically the design how to handle the material in continuous process and then how to have a kind of higher capacity screens without compromising on their effectiveness as well. So, there are many possibilities are available, there are different types of industrial screens are available. So, but here we see the screening equipment based on the type of the motion that has been generated. On those kind of basis we will be seeing some kind of a screening equipment, right. So, most common type of screening equipment are grizzlies or bar screens, shaking, vibratory, reciprocating or oscillating screens, or revolving screens or trommels also they are being known as. So, we see one by one. Grizzlies are used for screening larger particles of size greater than 25 millimeters. They consist of parallel bars with space to desired separations as per the requirement, and then in general to avoid the clogging or minimize the clogging, bars are often wedge shaped so that the clogging would be minimum, and they can be usually horizontally mounted or they can be inclined with an inclination angle up to 60 degrees. Vibrating grizzlies are also available for the feed material passing over surface in a series of jerks. Next one is the vibrating screens. So, vibrating screens are used as standard practice when large capacity and high efficiency are required. So, in the capacity section we are going to see for some of the ores, the capacity is so much high for this vibrating screen compared to other type of screens. The capacity of this vibrating screens is very much high. Similarly, their effectiveness is also very much high. That is the reason many people use these vibrating screens in their industries. Their capacity is large, especially for handling the finer sizes compared to the other screens, and then anyway the capacity is higher, and then especially if you wanted to separate out the finer material from the sample, then it is better to have a kind of a vibrating screens because their capacity is very much high if you are handling finer size material, not bigger lumps. Sample is having a finer material, finer powder kind of thing, and then if you wanted to do their fractionation, so then this vibrating screens would be better. Whereas the grizzlies are better if the samples are having very large particles like in few centimeters or few millimeters, etc. These vibrating screens can be mounted horizontally or inclined. In general, they operate at very high frequencies up to 1000 hertz, that is very high frequencies in general. It is having the advantage of accuracy of sizing, so and then low maintenance cost, and then saving in installation space. It requires very less installation space, and then maintenance cost is also small, and then the accuracy of sizing is also very much higher. That is the reason these vibrating screens have been used by so many people in the industries. In general, vibrating screens are used at a higher degree compared to the other screens. Then shaking screens consist on a rectangular frame holding wire cloth or perforated plate. They can be slightly inclined and suspended by loose rods or supported from a base frame by flexible flat springs, and then the frame is driven by reciprocating motions. The material to be screened is fed at the upper end, advancing by forward stroke of the screens. Then shaking screens conventionally used for both screening and conveying of number of materials. It is having the advantage of low headroom and power requirement, but it is having several disadvantages like high maintenance cost of the screen and supporting structure due to vibration. So, this is one of the big disadvantage, as well as the capacity is very low compared to the inclined high speed vibrating screens. So, vibrating screens capacity is anyway high, but compared to that one the shaking screens capacity is very much lower. Then reciprocating screens, they operate with a shaking motion, long stroke at frequencies between 20 to 200 hertz. They produce size fractions, removing coarse material first and then finest materials at the last. That is how these reciprocating screens are designed in general. They contain several decks of screens, one above the other, held in a box or casing as shown here. Let us say we have a box or casing here. So, there are several screens. So, only two screens have been shown here, the upper screen and lower screen like that, but there are the several screens one onto the other, such a way that the coarsest opening or the largest opening screen is at the top, and then the finest opening screen at the bottom. So, in that sequential manner they are arranged. In between these screens there are kind of ball cleaners are also provided. Okay. So, here what happens, the whatever the coarsest material, that feed that comes down here and then that passes through the surface, the top surface, whatever the finer material is there, that would be passing through the screen of larger openings, and then you can get a kind of different fractions in between if you have a kind of a large number of screens. Otherwise, if you have only two screens, you may have a coarse fraction coming at the top and then it is coming first, where after passing these screens the fine fraction is coming from the bottom like a last product. So, coarsest screen is located at the top while the finest is mounted at the bottom as shown in the figure, as I already mentioned here. The feed is dropped on top screen and screens and casings are gyrated in order to sift the particles through the openings. Whatever the particles are there, they will be passing through the opening, something like this, and then finer ones may be coming like this. The coarsest one would be coming from here. If you have the intermediate screens, I have not shown in the picture, there may be intermediate screens also. So, then you may be having the middle fractions as well. So, then horizontally gyrated screen design contains rectangular slightly inclined screens as shown, which are gyrated at the feed end, whereas the discharge end reciprocates but does not gyrate. So, what happens, the design is such a way that at the feed end, at the top end, wherever the feed is coming, that end is gyrated, whereas the reciprocation is taking place at the discharge end where the material is collected from the bottom as shown in the picture here. Right. So, because of this combination of motions, stratification of feed takes place, so that the fine particles travel downward on screen surface where they are pushed through the openings of screen by the larger particles moving on top. And then between the screens we have a number of screens. So, between the screens rubber balls are also provided and held in a separate compartment, so that to avoid a kind of any possible clogging. Right. So, here at this end a kind of gyrating motion takes place, and then at this end kind of a reciprocation motion takes place. Okay. So, because of this motion the particles pass through the surfaces screen opening, the finer particles passes through the screen opening like that, and then comes out as a fine material, whereas the coarse material comes first as a kind of the coarse fraction like given here, and then between the screens. So, these are the rubber balls are provided and they are given in a separate compartment, and then they move such a way that as the screen operates, the ball strikes the screen surfaces, so that whatever the opening of the material is there, that is being freed, if at all there is a possibility to have a kind of plugging. If any material is plugging those screens, when these balls striking those screen surfaces, those blocking or blinding of surface screen opening whatever is there, that will be cleared by removing those particles, either moving up and then going onto the surface of the screen, or passing through and then coming to the next screen like that. So, that is the purpose these rubber balls are provided, and they are striking the screen surface in order to avoid the possible clogging. That is the very much advantage of this particular reciprocating screens. Then vertically gyrated screens are also possible. They are designed such a way that casing is inclined at an angle between 16 to 30 degrees to horizontal plane. You cannot have a kind of more than 30 degrees. If you have a more than 30 degrees inclination, the capacity would be very much low, as well as the effectiveness would also be very much low. So, here gyrations are vertically about the horizontal axis. The principle is quite similar as whatever the horizontally gyrated reciprocating screen whatever we have seen. The principle is same here in vertically gyrated screens as well, but only thing that the casing is inclined at an angle of 16 to 30 degrees to horizontal plane, and then gyrations are vertically about the horizontal axis. Screens are rectangular shaped and fairly long. the speed of gyration and amplitude of throw are adjustable, as well as the angle of inclination is also adjustable. That possibility is there in the design. So, particular combination of the speed and throw would give a maximum yield of required product. It has been found that satisfactory separation into fine fractions one can get if having the inclination angle less than 20 degrees. If the inclination angle is less than 20 degrees, then separation of fine fraction is very much satisfactory by using this vertically gyrated screens. Then oscillating screens. So, here oscillating round screen is shown. Actually, they can be round or they can be square. In general, they are box like machines, either round or square, with a series of screen nested atop onto the other. So, we have shown only one screen here, and then there is a motor shaft which is having the elevation higher at one end and then lower at the other end, high weight at one end and then low weight other end. So, the feed comes here from the top and then through the screens. Through the screens it passes through because of the vibration that has caused because of the difference in the weight at the two ends of the motor shafts. Okay. So, that is the basic principle. The sieves are made of wire mesh or perforated screen decks can also be used depending on the size of the particles you are using. If the size of the particles are having bigger particles like in few centimeters or few millimeters, then you may prefer to have perforated screen decks which are having more mechanical strength. If the particles are having the more finer material, then you can go with a kind of woven wire mesh. They usually operate at gentle speeds between 300 to 400 oscillations per minute with a long linear strokes. So, vibration is accomplished by eccentric weights on the upper and lower ends of the motion generator shaft. So, whatever the motion generator shaft, this generator shaft is there. So, it is mounted on there are two different weights, upper weight and then lower weight. So, because of this one a kind of vibration is generated, and then because of that vibration the particle settling is taking place. So, the same figure is shown here. Rotation of top weight, whatever the top weight here, that creates a kind of vibrations in a horizontal plane which causes the material to move across the screen cloth to the periphery because of the vibrations are in a kind of horizontal motion, in a kind of horizontal direction. Okay. Then lower weight here that acts to tilt the machine, because of that one vibration is causing in vertical and tangential planes. So, because of this different weight at two ends of the motion generating shaft, what we have the vibration both in the horizontal direction as well as the vertical and then inclined tangential directions we have the vibrations, right. So, this is very advantageous thing of this particular design here, and then the angle of lead given between the lower weight and then upper weight, it provides the control of spiral screening pattern, and then speed and then spiral pattern of material travel over screen cloth can be set by the operator for maximum throughput as per the experience of the process engineer handling this particular equipment. So, there is nothing kind of generalized one. Next one is reels or trommels. So, they are usually revolving cylindrical screens mounted almost horizontally with one extreme opened as shown here. So, we have a single drum revolving screen here, we can have the multiple drum revolving screen also. Here one particular drum we have the different screens are covered, right, finer one, then medium one, then the coarsest one, like that. So, the feed is coming from here, and then accordingly based on the screen opening the material is being collected and then taken as a kind of discharge. The screen surface may consist of wire mesh or perforated sheets. Hexagonal cross sections are also used in general, since these lead to agitation which aids the separation of fine materials. Then feed material travels through the openings increasing in size. So, we can see the size here increasing, the smaller one, then the middle one, then the larger opening kind of thing. So, the feed material travels through the openings increasing in size along the drum, then discharged by a chute on the lower extreme of the equipment. We can have multiple drums revolving screen. So, several arrangements of trommels can be possible two of them are discussed here. One is the parallel type revolving screen and then another one is the concentric type revolving screen. In the parallel type revolving screen, we have shown here pictorial representation is given here, right. Simplest one is shown here when the drum perforations are uniform all over the surface. Here what we can see, let us say only 3 drums are shown, we can have a n number of drums with different openings, but the thing is that the openings in each drum they are uniform. Here you can see the first one, the coarsest opening is there, and then here the medium opening is there, and then bottom most one is a kind of a very much smaller opening is there. But within each drum the uniformity of the screen openings is there, okay. And then they are arranged such a way that maybe the largest opening screen drum, that particular drum having the largest opening is at the top, and then the drum having the smallest opening is at the bottom. That sequence we can order, we can arrange in other way also. So, to separate different fractions of a given material, drums are mounted in series as shown here in parallel type revolving screen. So, obviously 2 alternatives are possible depending on the largest perforation drum is located at the first of the series or at the top of the series or at the last of the series, in what way they have been arranged. Let us say if you arrange the largest perforation drum first of the series like at the top as I shown here in the picture, then the most convenient arrangement is to place the drums on top of the other, so that the finest fraction of material can be flowing to the subsequent following screens successively, and then finest can be collected at the bottom. If the largest perforation is the last one in the series, then the coarsest fraction advances to the next drum, and then convenient arrangement for this purpose would be having them one right after the other as a series consecutive drum screen. We can also have the concentric drum arrangement as shown here. So, we have a concentric arrangement of drum one into the other, a kind of concentric arrangement is there. The advantage of this particular design is that the compactness, you have a kind of compactness, but the problem is that the concentric drum or concentric arrangement is made such a way that the largest opening drum is at the center, and then the smallest opening drum is at the outer of the surface, I mean like last one. The largest opening screen at the center and then smallest perforation screen is forming the outer periphery. Because of this one, what happens, the feed enters at the center, so the smallest screen area will handle the complete load, that is the kind of problem. However, smaller fines fraction will progressively processed into the larger screen areas and then collected as the finest fraction. Let us say you have several concentric drums of different openings. In a sequence manner they are arranged such a way that the largest perforation is at the center and then finest one is at the end. So, from the center you get the coarsest fraction like this, from this particular section you get the finest fraction, in between you can get the medium ones also, medial product also you can get. So, these are the common types of screen equipment we have seen. There may be many other different types of designs available in industries also. So, we are not getting into those details of industrial screens. One can go through the book by Brown et al. As one of the reference I have given, or there is a book by Faust et al. So, that also gives many details about these industrial screens. Now, what we do? We see the effectiveness of the screens. So, there are several ways of reporting effectiveness of screens and all of them give different values. So, one should be careful when using these numbers. So, we take 3 different methods. First method, it is based on the recovery in the product of desired material in the feed and the rejection from the product of the undesired material in the feed. So, this is the basis for the defining the effectiveness in this particular method 1. So, let us say Xp is the mass fraction of desired material in the product. Let us say F is the feed and then P is the product material and then R is the rejection material. So, in the feed product material, what is the mass fraction of desired material? It is true that when we do the screening, the effectiveness is not 100%. So, in oversized material there may be some kind of undersized material also present, and then because of the screen tearing or tearing of the treen etc., or kind of breaking of the screens, you can have undersized material also, sometimes have the oversized material. So, it is not possible that if you have the product that only the required size material will be there. It is not true that in the rejection only the rejected size material will be there. In any fraction, if you take feed, product or rejection fractions you take, all the materials will be there, desired, undesired materials will be there. Here in this context of the screen effectiveness, desired, undesired are in terms of the size. Let us say for your application the size 400 to 500 micron is a kind of desired one. So, whatever the material that 400 to 500 microns is there, that is taken as a kind of a desired material. So, how much fraction of material in the product is having 400 to 500 micron size, that is XP. Okay. So, similarly, how much fraction of material is having size 400 to 500 microns in feed is XF. Likewise, how much fraction of the material having size 400 to 500 microns in the reject is XR. This 400 to 500 microns I have taken as a reference in order to explain, it can be any number, the desired size of the particle could be anything, right. So, now here P is the total mass of the product, and then F is the total mass of the feed, and then R is the total mass of the reject. So, recovery should be P by F multiplied by XP by XF. Then rejection should be 1 minus recovery of undesired material. So, that should be 1 minus P by F multiplied by 1 minus XP by 1 minus XF. Okay. Then effectiveness is nothing but the product of these two. So, when you multiply them, you get P by F XP by XF multiplied by 1 minus P by F 1 minus XP by XF. This P, F are kind of suffix, they are not multiplication. This is X suffix P and then this is X suffix F. However, difficulty in using this equation is one has to know the weight of entire feed and product, which is not practical in continuous process. We have seen several screening equipment, we have a kind of they are continuous mode operations. In industries you prefer to have a continuous mode operation so that you can handle large amount of material in a lesser time, right. So, though in a laboratory screens you can have the metal stakes with the individual metal pans having screens at the bottom, you can arrange and then do the things and then you can find out what is the feed weight, what is the product weight, like that you can do, but in industry that is not possible in general. Okay. So, that is the one of the important drawback of this method, that is you should know what is P, what is F, otherwise you cannot use this equation, right. Another thing is that how to decide whether the oversize is product or the undersize is product, that is again a problem with this method. So, now we go to the second method where it overcomes the requirement of knowing the feed and product weights in continuous process, right. So, that is what we do here. So, how we do here? We do by a simple material balance. So, if you do a overall material balance, let us say feed whatever is coming, that is being separated into the product and rejectant, right. Then if you do the fractional balance for the material around the screen, then you have XF multiplied by F is equals to XP multiplied by P plus XR multiplied by R. Now, here you can write R is equals to F minus P like this, then you can rearrange this equation. So, you get P by F is equals to XF minus XR divided by XP minus XR, that is it. Simply this P by F you substitute in the previous equation number 3 of method 1. So, you will get the effectiveness by this method 2, where you do not need to know the weight of the feed or weight of the product or weight of the rejectant. You can know only based on the mass fraction alone obtained by the screening method. So, when you substitute this P by F in equations 1 and 2, you get recovery as P by F XP by XF is equals to XF minus XR by XP minus XR multiplied by XP by XF. Same is rejection is 1 minus recovery of undesired material. So, that comes out to be 1 minus XF minus XR by XP minus XR. So, this supposed to be whatever the P by F that we get, and then multiplied by 1 minus X suffix P and then X suffix F, like that is the mass fraction of the desired material in the product and then mass fraction of the desired material in the feed. Okay. Then effectiveness would be the multiplication of these two. So, you will get this one after simplification. So, this is by the second method. Another method, method 3, it is based on the product of recovery and enrichment, which gives the effectiveness as this one, equation number 7. We take couple of problems and then try to calculate effectiveness by these different methods and then see how different numbers we get by 3 different methods. Example 1. So, let us say a quartz mixture having screen analysis shown below in table is screened through a 10 standard mesh screen. The cumulative analysis of overflow and underflow are given in the table, right. Calculate the mass ratios of the overflow and underflow to the feed and the overall effectiveness of the screen, that is P by F, R by F you need to calculate, and then you need to calculate what is the effectiveness. So, this is the information is given a table, it is given in the problem, mesh versus DP information for a feed, overflow and then underflow is given under the cumulative fraction smaller than DP information. 4 to 65 mesh and then pan have been used, and then the reference screen is 10 mesh screen. So, from here what we get, this should be your XF and then this should be your XP and this should be your XR, right. So, you know XF, XP, XR. So, you can calculate recovery, you can calculate rejection, you can calculate even the effectiveness. So, we use method 1 for 10 mesh. Why are we taking 10 mesh? Because that has been screened through 10 mesh, that is the problem statement is given. So, that is the reason we need to take these numbers XF, XP, XR corresponding to 10 mesh. Okay. So, for that only we need to calculate the recovery and then rejection. So, P by F is recovery, XF minus XR by XP minus XR, when you substitute you get 0.42. Rejection is R by F is XP minus XF by XP minus XR, when you substitute these numbers you get 0.58. Then effectiveness, this expression by method 1, if you substitute you will get 66.9% effectiveness. We will take another example. Data on screening operation is presented in below table. Particle size distributions of feed, overflow and underflow are given as cumulative frequency. The screen used for separation has an aperture size of 460 micron and 100 kg per hour of feed and processed obtaining 650 kg per hour of overflow. Calculate the efficiency of the operation. So, here data for the table is given, sieve aperture size in microns is given and then cumulative fraction for the feed, coarse and then fine material are given. But here the screen used for separation has an aperture size of 460 micron, that is what it is mentioned. So, corresponding to 460 microns we have to take XF, XP, XR. So, but here 460 micron opening, the information directly it is not given, and then you cannot interpolate also because you cannot know what is the trend between the sizes and fractions etc. So, for that what you do, you plot this cumulative fraction of feed, coarse and fine with respect to the sieve aperture opening or particle diameter or opening of the sieve, then corresponding to 460 microns from the graph you can take the XF, XP, XR. So, first we do the cumulative analysis, cumulative mass fraction versus aperture opening in microns we have plotted. The middle one is kind of feed and then the upper one is kind of coarse material and then bottom one is kind of fine material. So, the screen that has been used for separation is 460 microns. So, you draw a kind of vertical line at 460 like this, and then whatever the corresponding that values are there, let us say feed curve wherever it is intersecting, that you take as XF. So, that is 0.58. Then similarly, the coarse one is coming as a kind of 0.85 and then the fine one is coming as 0.14. From material balance, the feed is given as 1000 kg per hour, R is also given as 650 kg per hour. So, P you get as 350 kg per hour. From here, from this graph, For DPC 460 microns, we can get that XF as 0.58, whichever is, let us say, when you have this vertical line at the point where it is intersecting the feed curve, the corresponding value mass fraction in the y axis, that should be taken as XF, that is 0.58. Similarly, XR at 460, when you draw a vertical line wherever it is intersecting the fines, and then corresponding y axis value, that should be taken as XR, that is 0.14. Likewise, XP is 0.85. So, now you have 0.58, 0.14, 0.85 as XP, XR and XP. So, all three are known. So, then you can calculate the effectiveness. We calculate using all three methods. Method 1, that is equation 3, if you substitute, you get E is equals to 0.449. Method 2, equation 6, if you substitute this XP, XR, XF values, then you get E is equals to 0.7068. Method 3, if you substitute these values in equation number 7, you get these values are 0.5839. So, here this XF is suffix, here also XP is X suffix P and then X suffix F. So, now you can see all three methods are giving three different values of the effectiveness. Last example, it is desired to separate a mixture of crystals into three fractions. Let us have a coarse fraction retained on 8 mesh screen and then fine fraction passing through 14 mesh. Whatever the middle fraction is there, that is passed through 8 mesh but retained on 14 mesh. Two screens in series are used, and 8 mesh and 14 mesh conforming to the Taylor standards, that is whatever the mesh opening for 8 mesh is there from the Taylor series, that should be taken as the DPI. Similarly, for 14 mesh, whatever the Taylor screen opening is there, that should be taken as the DPI for the 14 mesh. Screen analysis of feed, coarse, medium and fine fractions are given in the table below. Assuming the analysis are accurate, what do they show about the ratio of weights of each of three fractions actually obtained? So, how much of coarse material is obtained, how much is the medium obtained, how much is the fine fraction is obtained, that we have to calculate with respect to the feed. So, let us take feed as a kind of 100 kgs basis. So, this is the table is given, the screen versus feed and then coarse fraction, middle fraction and then fine fraction, their corresponding mass fractions are given here. They are not cumulative one, but they are differential one. So, when you add them together for all 4 cases, you get the kind of 100. Now, let us have a designations. Whatever the coarse material that is retained on 8 mesh, you take it as A. Then whatever the intermediate material that is passed through 8 mesh but retained on 14 mesh, you take it as B. Similarly, whatever the fine material that is passing through the 14 mesh, you take it as C. So, this is labeling, this is not the weights. A, B, C are a kind of labeling, they are not the weights. Now, coming to the weights, take 100 kg of feed, then let DC is the coarse material produced. How many kgs of coarse material produced, that you take DC. How many kgs of medium material produced, that you take DM. How many kgs of fine material produced, that you take DF, which is nothing but 100 minus DC minus DM. Now, from the screen analysis, we just get back to the screen analysis one here. So, the feed is containing all three materials. Similarly, coarse fraction is also containing all three materials. It may be having coarse material, it may be having medium material, it may be having fine material also, because 100% separation is not taking place by any types of screens, right. Same is true for the middle fraction, same is true for the fine fraction also. So, what we do, first we take how much fraction of what is the material of fine fraction present in the feed, coarse fraction in the feed and then medium fraction in the feed, that you take. Similarly, in coarse fraction, what is the amount of fine, what is the amount of coarse, what is the amount of medium, that you take in this fraction also. Likewise, in middle fractions, fine fractions also, all three types of materials may be there, right. So, that we are going to see now here. First, what we do, we take a feed. From the screen analysis of feed, what is the coarse material that is being retained on 8 mesh. Okay. So, whatever the corresponding mass fractions are there larger than 8 mesh opening are the smaller mesh numbers. So, that is 3, 4, 6, 8 mesh numbers whatever are there, whatever the material retained on that particular up to 8 screen, that is all should be taken as A. So, coarse material is, how much coarse material from here from the in the feed, it is 46 kgs, that is 3.5 plus 15 plus 27.5. Similarly, that is the medium one, that is passing through 8 but retaining on 14. So, that should be the summation of 23.5 plus 16, that is 39.5 kgs, and then what is the fine? It is all the remaining, that is passing through the 14, that is all remaining is a kind of C fine material, that is 100 minus 46 minus 39.5. So, that is 14.5 kgs. Similarly, in coarse product also we can have AC, that is up to 8 mesh, whatever is there, that is the coarse. So, that is 14 plus 50 plus 24 divided by 100 multiplied by DC. Multiplied by DC is nothing but 0.88 DC. Similarly, medium one is that between these two, that is 8 by 10 and 10 by 14. So, corresponding coarse fractions are 8 plus 4 divided by 10 multiplied by DC, that is 0.12 DC. And then fine fraction here passing through 14 mesh is not there in this coarse fraction at all. So, at least in the coarse fraction the fine material is not there, only coarse and then medium material are there. So, here you can see all the DCs are there, we are doing balance for the DCs in the coarse product. Similarly, middle fraction also, if you do in the middle product, you have what is the coarse fraction in the middle product, that is up to 8 mesh, that is 4.2 plus 35.8 divided by 100 multiplied by dm, that is 0.4 dm. Similarly, what is the medium fraction in this middle product is Bm is equals to 30.8 plus 18.3, because that is passing through 8 and then retaining on 14 is designated as a kind of medium one. So, 30.8 plus 18.3 divided by 100 multiplied by dm is equals to 0.491 dm. And then what is the finer ones in this middle fraction, whatever that is passing through 14 mesh, all should be considered in a kind of finer. So, that is Cm is equals to 10.2 plus 0.7 divided by 100 multiplied by dm is equals to 0.109 dm. Similarly, in the fine product, the material retained on up to 8 screen, there is nothing. So, that is 0, AF is equals to 0, and then medium fraction, that is passing through 8 but retaining on 14 is having 20 plus 26.7 fraction. So, 20 plus 26.7 by 100 multiplied by df. So, that is coming as 0.467 df, we can write 100 minus dc minus dm, because dc plus dm plus df is equals to 100, that is feed. Okay. Similarly, Cf is that in the fine fraction, what is the finer material is there, all that passing through 14 mesh is all counted as a finer material. So, 20.2 plus 19.6 plus 8.9 plus 4.6 by 100 multiplied by df, that is 0.533, again df we can write 100 minus dc minus dm. So, now if you write the A balance, A should be A is equals to AC dc plus AM dm plus AF df. So, when you substitute this, you will get this equation, and then B balance should be B is equals to BC dc plus BM dm plus BF df. So, you get this equation. Then similarly, C balance is nothing but C is equals to CC dc plus CM dm plus CF df. So, you get this equation. So, if you solve equation 1, 2, 3, you get dc is equals to 24.9 kgs, dm is equals to 60.2 kgs and df is equals to 14.9 kgs. So, we can understand from this operation, it is doing such a way that 60.2 kgs medium fraction is there, and then 14.9 kgs of finer fraction is there, whereas the coarse fraction is 24.9 kgs. So, this is how we have to solve the problems using this screen analysis. Capacity of screens. Capacity of screens and effectiveness are very much closely related. If a low efficiency or effectiveness may be tolerated, then screen may be operated at high capacity. right. So, it is very difficult to have both high capacity and then high effectiveness simultaneously. So, if you wanted to handle high capacity material, large amount of material, then you must be compromising in the effectiveness. Ability of the device to prevent blinding of screen surface is probably the most important factor determining the capacity of the screen. So, in general, blinding is a very important problem that one come across in the screening. So, sometimes whatever the screen opening is there, that may be blocked by the particles of larger size or something like that. So, that particular effective area that is available for the passing of the material, now that is reduced. So, because of that one, the effectiveness decreases. So, the capacity of the screen also decreases. So, in the dry screening, if the moisture or the dampness is more, then the capacity would be very small, because in the dry screening we not necessarily dry the material, but whatever the naturally available material we get, so that must be having some moisture. If that moisture is more than permissible limit, then the capacity would be very much lesser. And then because of greater surface area, finer material can tolerate a greater percent of the moisture in general. If feed contains a higher proportion of material of a size just slightly smaller than the size of the opening in the screen, that is near mesh material we call it. Let us say mesh opening is 0.05 mm, but if you have some material like 0.049 mm or 0.048 mm material, then it is possible that those may be blocking the pores in general. So, then capacity of those screen would be very much reduced because of those kind of materials. So, it is not advantageous to having near mesh material when you do the separations. The ratio of the open area of the screen to the total area is an important factor in determining its capacity. So, whatever the individual square apertures are there here, like like this, those square aperture areas, and then all of the area, that is effective area of the entire area, total area of the screen. So, the ratio, whatever the ratio is there, that ratio of open area of the screen to the total area is also going to determine its capacity. Then, because the screening capacity depends upon the area of the screen surface and then screen aperture, the capacity is usually expressed as the tons of feet per square foot of screen area per millimeter of screen aperture per 24 hours. Approximate capacity of screens for dense materials such as ores are given here in this table. Type of screen and the capacity range in tons per square foot area per mm aperture per 24 hours it is given. So, the grizzlies we have seen, so they have the lowest capacity 1 to 6. Stationary screens in general they have for these ores 1 to 5, whereas the vibrating screens, as we already discussed, having the high capacity and then high effectiveness, we can see here also for these ores 5 to 20, and then shaking and then oscillating screens 2 to 8, whereas the trommels have the lowest capacity of 0.3 to 2. How to convert them into the number, how much of weight can be handled per hour or per day, something like that. That is, let us say now vibrating screens is having 6 square feet of the surface and an aperture of 2 mm. That is, you take a vibrating screen which is having 6 feet squares of area, surface area, and then opening of that aperture, whatever the screen opening is there for that vibrating screen is only 2 mm. Then according to this one, the capacity should be 5 to 20 multiplied by 6 multiplied by 2. So, that you get 60 to 240 tons of ores per 24 hours it can handle. So, it can handle 60 to 240 tons of ores per 24 hours. Factors leading to inefficient separation, rapid feeding. Rapid feeding is a kind of problem. We have seen a kind of continuous screen. So, where we do a kind of feeding continuously. If you feed rapidly, so then also inefficient separation may take place. And then steep angle of screens, we have seen that the mounting can be inclined also. If you take the angle too steeper angle, then also the separation may not be efficient. Then one must provide the sufficient time for the complete separation, otherwise if you provide insufficient time, the separation may not be efficient. and then excessive dampness in the feed may cause cohesion of small particles to form large masses or adhesion of small particles to larger particles. So, in such cases also efficiency is very poor. Sometimes wound screens with enlarged apertures may pass oversized material into the undersized fractions also. That is also causes inefficient separation, and then sometimes blinding or clogging of screens takes place because of the blockage of the screen openings. Then they may retain more undersized material in the oversized fraction. So, then also inefficient separation would take place. So, this is about the screen analysis, screening, screen analysis, screen equipment, and then effectiveness, and then capacity of the screens. All the details required at the UG level about the screen processes have been discussed in this particular module through lectures 4, 5 and 6. The references that have used have given here: McCabe-Smith, Ortega-Rivas, Richards and Harker, Giancopoulos, Brown et al., Badger and Banchero. The some of the schematics and problems are taken for this lecture from this unit operations of particulate solids theory and practice by Ortega-Rivas. Likewise, some problems are also taken from the Richards and Harker and then McCabe-Smith. Thank you.